let's start with a single dish radio telescope, the kind of thing that Nissim has been talking about, a parabolic dish of diameter d. And if we schematically show its sensitivity as a function of direction, it has a main lobe in some direction, and then it may have side lobes in other directions. And the main lobe is basically typically along the axis. You'll have to forgive my drawing. And it has a characteristic width, which we could call theta 0, or if I want now, I'll just call it delta theta for consistency. And that characteristic width, delta theta, will be of the order of lambda by d. Right? So that means we are sensitive to radio emission from sources which lie within delta theta. And we could, to zeroth order, we assume that any radio sources which lie within delta theta, that emission will be received and picked up by the dish. And any emission which lies outside of delta theta, we are not able to see. We don't receive it. We are not sensitive to it. So with this delta theta, we could regard in two ways. We could either regard it as the resolution of this telescope, or we could also call it the field of view of the telescope, because that's all it sees. Right, and this delta theta we also worked out, for the typical largest radio dishes that we have around at wavelengths of the order of 20 centimeters. And we saw that it would be typically around a few arc minutes in size. And we saw also that that is actually a very coarse resolution. And we would like much, much higher angular resolution in order to be able to do, modern astronomy. And that we saw was achieved through interferometry. So let me just draw again a schematic of what we looked at yesterday. I beg your pardon. Let's draw a schematic of what we looked at yesterday, which was like this, that let's say I have now two dishes. Separated by a distance x. And they're looking at some distant field over there. And the center of the field makes an angle theta 0 to the vertical. Then we saw as far as rays from the center of the field are concerned, that is the rays that I have drawn, it reaches antenna 1, that ray reaches antenna 1 before it reaches antenna 2. So if the voltages which come out from these antennas are V1 as a function of time and V2 as a function of time, then V2 will be a delayed version of V1 because that ray has to travel this extra distance. The extra distance being x sine theta 0. And the delay itself that it suffers, which we call the geometric delay, will be and this distance is of course x cos theta 0. And we saw also that if we construct the following apparatus, which takes these two voltages and multiplies one with the complex conjugate of the other, and integrates it for some time, it produces an output which we call a visibility. where V of u will be equal to with u being the projection the projected component of the baseline in units of wavelength, and L being basically the position of the source, angular position of the source. We had called it delta theta and then redefined it as L. And we have that L, that plus theta 0 minus delta theta by 2 less than, it was under this approximation that all of this worked. Which is a Fourier transform relation. So I'll pause here, as was just a summary of all the stuff we did yesterday. And I can take, if there's something which came up, after my lecture yesterday, or something that you had wanted to ask yesterday but didn't get a chance, we can pause.
Sir, yesterday you defined something as V tilde also. So what was that?
Yes. So that V tilde is the same thing that I'm now for sure, just to be saving time, is the same thing that I'm calling V of u now. Do you want me to go back to what was the difference between V of tilde and V of u?
No, sir. You could provide the PDF for the sheets of yesterday. It would be better.
I have sent that to Saikya. I can show it on the screen also. But okay. Do you want, yeah. The difference, if you remember, when we were talking about V tilde and V of u, was the following, that we had originally defined, I think at that time we were, maybe it's easier if I just, go back to yesterday's sheet. So this is yesterday's sheet where we discussed V of tilde and V of versus V. And V of tilde was basically when we had multiplied the V that we got with this phase term, which came from the geometric delay at the center of the field. You remember that we had to get rid of it, because if we hadn't got rid of it, when we averaged over frequency, we got a zero output. So to avoid that, we had multiplied it with this term, right?
Yes.
And that we call V tilde. You remember that now, right?
Yes, yes.
Yeah.
Thank you.
Yeah. So that term we had introduced just so that we can average over frequency without losing the signal, which, and as you remember, we need to average over frequency so that we improve our sensitivity. Is there anything else? Anything else anybody else would like to ask? All right, so if not, then maybe we'll press ahead. Now, I'd like to make a couple of points over here when we go back to this picture. Just give me a moment. Right? So we've got a field of view that we are looking at, which is at an angle theta 0 to the baseline vector x. So that vector between the two antennas is called the baseline vector. And the field that we are looking at is at an angle theta 0 to this baseline vector. So as you would see, if you're dealing with two antennas on the surface of the Earth, then the source from our perspective is going to rise and set. Right, so that means that theta 0 will change. That theta 0 will change from minus pi by 2 when the source is rising, to 0 when it is overhead, to pi by 2 when it is setting. Right? So that theta 0 is going to change continuously all the time. So that that correction term that we just saw, right, that e raised to the power of j 2 pi nu tau g naught, which I have to multiply the visibility by, which is called delay tracking, that will have to be changed all the time, right? Because the angle is changing, that term also has to be corrected all the time, which is something that the correlator does. And so this basically, this particular operation over here, the device which does, just hang on, let me just find my cursor. Yeah, here it is. So basically this, the device which does this operation is called a correlator. Right? And what we've drawn actually is a very bare bones correlator. In real life, the operation is slightly more complicated than this. And that has to do with multiple things. It has to do with the fact that as we saw that delay will change with time all the time towards the phase center. And so I have to correct it all the time. That's something called delay tracking. It has to do with the question that somebody asked me in between as to whether we use IF frequencies here or not. And indeed, we do use local oscillators and IF frequencies. And that also changes the signal processing over here slightly. And finally, it has to do with the fact that we want to measure the visibility not just at one frequency, we want to measure it at a range of frequencies. So the output will not be just one number, but it will be a number at each frequency that we are interested in observing the sky at. So the visibility will be a function of U and of frequency. Right. So, all those operations are done in the correlator, which makes it a slightly more complex instrument than what we've drawn over here. But the one thing I did want you all to bear in mind right now is that that delay that we spoke about will have to be tracked as the source rises and sets. The other thing which I want to draw your attention to is that U also depends on cos theta 0. Right? So that means as the source rises and sets, this U also changes. Right? So even if I have antennas at a fixed separation on the Earth, that is X is not changing, the variable in this integral, U, is going to change as the source rises and sets. And we also saw what this integral is formally called, and somebody had named it for me. So what is this kind of integral called? Yeah?
Fourier transform.
It's called a Fourier transform, right? And I'm going to extend the limits of the integration from minus infinity to infinity so that it is formally a correct Fourier transform. And I am allowed to extend these limits from minus infinity to infinity because my radio telescope has zero sensitivity outside of delta theta. So I can just, whatever the brightness is there within the field of view, I can extend from minus infinity to infinity just by putting zero everywhere else outside, because I can only see the part within minus delta theta by 2 to delta theta by 2. I can just extend that function I of L by putting it to be zero everywhere else outside. So now this is formally a Fourier transform. And the interesting thing about the Fourier transform is that it's mathematically invertible. That means if this is the relationship between VU and IL, and I'll remind you that this is what we have measured. Our correlator gave us this. This is what we want, which is the image of the sky. Right? Then this relationship basically implies that I of L, because your Fourier transform is invertible, is given by this relation, the inverse Fourier transform. Right? So that means if I can measure V of U, I can measure I of L. And we did all of this basically in one dimension, but it's straightforward to extend it to 2 dimensions, in which case the relationship will be the following. It will be a double integral. But, I'll probably not write the double integral all the time. I'll just write one. Sorry. Which means, again, that the 2D image of the sky that I want is simply given by this relation.
So just wanted to point out an error that in the IL it will be DUVS.
This one, right? That's what you wanted to point out, what
Yes.
I just fixed? Yeah,
Yes,
that's
yes,
correct.
sir.
Yeah, that's correct. Thank you for that. Yeah. So, so this tells us basically now how to make an image of the sky. How do we make an image of the sky? I'll have these, I could, for example, supposing I have 2 antennas, I can take these 2 antennas, I can put them at some separation, and I use my correlator to measure, one particular visibility at one particular U and V. And if one of my 2 antennas is movable, then I move it to a slightly different position. I do another measurement that gives me V at another U and V. And I can go on and on and on until I have built up measurements of V, U, V. That is, I know the function, which is called the visibility function VUV. Once I know the visibility function VUV, I can invert it and I can get the sky distribution. So that's basically how interferometry works.
What's M here?
So M would basically L and M, because when I drew that picture for you, I was working in basically the plane of the paper, right? We had only one angle, theta 0. Right, but in reality, we are working with the sky, which is a sphere, a 2D sphere, right? I mean, the spherical surface can be described by 2 angles, theta and phi. And so I will need 2 numbers to tell me where on the sky the object is. And those 2 are L and M. You can think of them roughly as d theta, and delta phi to tell me the location on a 2D sphere.
Okay, sir. And how does the new visibility function differ from V?
I beg your pardon? Your voice?
How does the new visibility function, like V as a function of U and V, differ from the VU that we found previously, except for the integration that we are doing again?
It doesn't. So I just I did that whole derivation for you, assuming that we are living on the on a plane, on a sheet of paper, and the sky basically is a circle. But in reality, the sky is not a circle; it's a sphere. And so if we were to redo that whole calculation for a sphere rather than a circle, because we just assumed a circle right now, right? One theta would tell me where the source is, but actually I need theta and phi for a spherical sky, right? I haven't worked through the algebra, but I just wrote down the expression that you would get for it, and this is the expression.
Okay, thanks, sir.
Yeah, that's clear, I hope.
Yes, sir, thanks.
Okay, so now if that's clear, then let me just show you, maybe a few pictures. So I think you may have seen this picture before, but I mean, or a similar picture, but anyway, let me just show that again. I mean, so this was what we started with, a single dish radio telescope. And this in particular is the GMRT dish. And so the dish itself is that paraboloid that you see over here. You can see the ribs, that umbrella-like thing is the dish. But the dish you want to be able to move and point anywhere in the sky. And so the dish has to be mounted on a mechanical support. And that particular mechanical support is designed such that you can rotate the dish about 2 axes. And therefore, you can point it anywhere in the sky. It's a parabola, and so therefore rays which come along the axis of the dish get reflected and go to the focus. It's a prime focus, as Nissim told you. And at the prime focus, there is a feed antenna which converts that radio wave into a voltage, which is then amplified and processed further. And as Nissim probably told you, there's not just one feed antenna, there's actually 4 feed antennas on a rotating turret. And depending on which frequency band you want to observe, you can rotate the desired feed to point towards the dish. And therefore, that is the feed whose signal you will pick up and further process. Right. So this is one element of our 2-element interferometer, or one element of an interferometer. In the case of the GMRT, there are actually 30 antennas. So this is one out of the 30 antennas that we have. And again, to summarize what we have done yesterday and just looked at briefly today, you get a high resolution image by correlating the voltages between 2 spatially separated antennas. And what this correlation does is to measure, we saw that formally, a single component of the Fourier transform of the image under suitable approximations. And what were the suitable approximations? Right now, we've looked at one of them, which is that the field of view has to be small, that delta theta had to be small, right? But small compared to pi. We did this whole derivation under that approximation. And in that case, the antenna pair is like a filter. If you had a filter working on a time domain signal, for example, a filter which works on audio signals, it'll pick out one particular tone and it filters out all the other tones. One particular Fourier component of the Fourier transform of the audio signal. And the antenna pair is very much like that. It's like a filter. It's picking out, but now one spatial frequency component of the Fourier transform of the sky distribution. And for those of you who've studied Fourier transforms, you would be aware that if I had, that there's an inverse relationship between the Fourier variables. And so if I have a wide pair of antennas, it would pick out high spatial frequencies, whereas closed pairs pick out low spatial frequencies. For those of you who haven't studied Fourier transforms, I'll just mention that a consequence of that integral relationship that you saw was that if my antenna pairs are close together, it's basically sensitive to a very long wavelength oscillation on the sky. Whereas if the antenna pairs are very far apart, it is sensitive to a very short wavelength oscillation on the sky. So that means if I want to image a source which is large, which has slow oscillations on it, large scale oscillations corresponding to a diffuse extended source, I will need antenna pairs which are close together. Whereas if I have a source which has a lot of fine structure in it, which therefore has very high frequency spatial components, I would need antenna pairs which are very far apart, right? And so in this sense, this imaging is quite different from what because it's an indirect imaging. It's a little different from what you normally think of as imaging. Normally we have a 2D detector and it just a pixelization of the detector determines, along with the optics of the lens or whatever you put before it, would determine the resolution and what components you're sensitive to and so on and so forth. Here, the separation between the antennas tells you which components of the image you are sensitive to. So since the imaging is indirect, it could quite well be that if your antenna pair separation is not well tuned to the problem, you will see only a filtered version of the image. And so the image, there may be certain components of the image, brightness, which you simply are insensitive to because you have filtered them out. You don't, the equipment that you have is not sensitive to it. I mean, if you're thinking in the color domain, you could imagine it's, just to give a very rough analogy, it would be like an object which is emitting in green light, but you put a whatever blue light and you put a red filter in front of your camera. You won't see the object, right? Because you filtered out the light of the object. And similarly over here, we are doing a filtering, but we are doing a filtering on the on the structure of the object. So there may be certain elements of the structure which you don't see because you have filtered them out. So if you really want a high fidelity image, you need good sampling. You need to make sure you've picked up all the frequency components which are of relevance. And so you need both close and distant antenna pairs. And how could one arrange that? So, the very simplest way to start would be, as I had described right at the start, that we are looking at sources which, apart from a few, sources which vary on very rapid time scales like pulsars and so on, most of the celestial sources that we're interested in simply do not vary on human time scales. At least there's statistical parameters, which like the visibility that we're interested in. The visibility is some kind of statistical, it's some average that we're doing, right? A statistical parameter about the source. So that means that I can imagine I could do the following operation using an interferometer. And I'm here showing you one of the very, very early interferometers set up at the Parkes radio telescope. So there's this big 64-meter diameter telescope, which you can see in the background. And a little bit in the foreground, you have a smaller antenna, which is mounted on a rail, right? So what you could imagine doing is you move the small antenna around on the rail. And you put it once very close to the big antenna, and you track a source from rise to set. As we saw when we tracked the source from rise to set, you will get multiple measurements because as the source rises and sets, that projected separation between the antenna changes. And so you do that one day. The next day, you sort of move your antenna a little bit and you do another sort of set of measurements and so on. In principle, you could do this, right? And then over a period of time, you would have measured a large number of these Fourier components, and then you could put that collection together, invert it, and make an image of the source, right? And I think I've also got a very schematic picture of what might happen if I have more than two antennas. And again, you should not take this very seriously. I just wanted to remind you of two things, that the field of view of such an instrument will correspond to that of a single element of the array, right? Because that we've been seeing from the start. And the second is that even though I have a high resolution, right, I've got a resolution which corresponds to the largest separation, the largest baseline that I have in my array, the collecting area does not correspond to, the largest separation of the array. The collecting area is simply the sum of the collecting area of all the elements in the array, because I'm not picking up any signal from regions where there is no antenna, right? So my resolution has improved dramatically, but my collecting area has not improved proportionately. And here, if you can see that animations is a very sort of, you should not take this too seriously, but it's just a sort of a zeroth order idea of what happens when the Earth rotates, right? As the Earth rotates, it's like the antenna array is rotating with respect to the sky, and therefore you will measure a large number of antennas, of baseline separations, instead of just measuring a few. The advantage, of course, of using an array is that if I had only a 2-element interferometer, I make one measurement at a time. On the other hand, if I have an n-element array, I would make NC2 measurements at a time. So this is basically how interferometry is done. I would take a field, I would observe it for a few hours with an array with a large number of antennas. If I have 30 antennas, for example, as the GMRT does, 30C2 is 435. So I measure 435 visibility points at a given time. And if I were to track the source from rise to set, the visibility points that I measure will go on changing. And so I'll finally get quite a good sampling of what would be called the UV plane. And once I have that, I would be able to invert it to get the image. So, let me just illustrate that for the GMRT. As I said, it's an array of 30 antennas, each 45 meters in diameter. It's located about 80 kilometers from Pune. And it is the most sensitive radio telescope in the world at most of its frequencies of operation. So I've just put that up on a map since y'all are from all over, just to show you. I hope you can see that very small antenna, which shows you roughly where the GMRT is located. And I'll show you now the configuration of the antennas. So there are 12 dishes which are in a central compact array located about 12 kilometers, 1 kilometer on a side. And there are 12 dishes in a kind of pseudo-random array packed in that area. And then the remaining dishes are spread on these roughly Y-shaped arms, which are about 14 kilometers across. Three arms, which make a roughly Y-shaped array. And so basically these things which are shown as dots at the center of the image, those are what would be called the central square antennas. And the baselines between the central square antennas, they're all relatively short. And so they give you sensitivity to diffuse a wide scale emission. Whereas the baseline between the arm antennas, which are all quite large, would give you sensitivity to, which give you very high resolution. So it would allow you to image compact, to see fine structure in sources quite well. So I'd like to pause over here and see if y'all have anything you'd like to ask or something that has come up or which wasn't clear before I go on.
So could you just explain what you said just now, like about the compact dishes and the arrangement of the antennas?
Yeah, I can say that. So this goes back to what I had said about the Fourier transform. So you are familiar with Fourier transforms?
Not that much, but yeah, I mean, kind of.
Okay, so we saw that V of U would be maybe I should put up that relationship again. I'll just stop sharing and try and put up my that thing. So this is the relationship that we are interested in, right? The one on the left-hand side.
Yes. Sir.
This is what we are measuring, and this is what is observed, right?
Yeah. Yes, sir.
Yeah. Now, the point of this relationship is that supposing I were the point I want to make about this relationship is that supposing I of L, for example, is a sinusoidal signal with a large wavelength. Okay.
Yeah.
Supposing that basically the image of my sky is such that there are no, I mean, it's quite smooth on small scales, but it's got some kind of variation on large scales. Right?
Yes, sir.
So it's an object which doesn't have much fine scale structure, but it has some large scale structure. It's only on large scales that I see some change. On small scales, it's very smooth. This integral is such that the V of U, which I will get when I do the integration, this V of U will be non-zero only for small u. It'll be zero everywhere else. For large U, the integral will give me zero for V of U. That's, if you work through the integral, which I'm not going to do, that's what you get. That's a property of the Fourier transform. And similarly, if I of L had fine scale structure, but not much large scale structure, that is, I see oscillations on fine scales, but on the large scale, basically on the average, there's really not much change, right? In that case, V of U would be a non-zero only for large U, whereas for small u, it would be zero.
Yes, sir.
Okay, that's the property of this. So that means if I want to image a source which has only variations on large scales, I should measure V of U on small u, because everywhere else V of U is zero.
Yeah.
And the reverse, if I want to image a source which has got fine scale structure but not much large scale structure, then I should measure V of U at large u. Right. And now supposing I have a source which has both these kinds of structures, then I should measure V of U both at small and at large u.
Oh, okay.
Right, I should, and that's correctly speaking what I should do, because in principle, I don't, a priori, I know a whole lot about the source. So ideally, what I really should do is to measure V of U everywhere from 0 to infinity.
Yes.
That's really what I should do. right? But I should bear in mind that if I do know something about the source, and I know, for example, that it has a lot of fine-scale structure, but not much large-scale structure, then I could happily not measure it at small u because I know that it's 0 over there. But if I know nothing about the source, I should measure it everywhere. And so that is the point I was trying to make when I was talking about this distribution of the GMRT, that I have antennas placed such that they allow me to make measurements at small u. I also have antennas placed in such a way that they allow me to make measurements at large u. So it gives me measurements which span, they give me good sampling across the entire range of u. Other telescopes, such as, for example, there's a very large array in the USA, they follow a different strategy. What they do is that they put all of their antennas on rails. And so if they want to image a source which has got large scale structure, but not a whole lot of fine scale structure, they move all of the antennas in towards the center and they make those measurements. On the other hand, if they want to observe a source which has got fine scale structure, but not much large scale structure, they move all of the antennas out on the rails and they measure the V of U at large U. And if you had a source which shows all these kinds of structures, then you have to do multiple measurements. You have to do a measurement when the antennas are close in, another one when the antennas are further out, and so on and so forth, until you finally cover both small and big U. At the GMRT, there's been a slightly different approach taken where the antennas themselves are placed in such a way that about half of them give you good coverage at small u and another half give you good coverage at large u.
So V of U was non-zero for small fields, like when U is small.
When I say no, it's not so much about, yeah, no, go ahead, please go ahead.
No, I was confused whether V of U is non-zero for small values of U or for large values of U.
It depends on the source. If the source has fine scale structure, V of U will be zero near the origin. Whereas if the source does not have fine scale structure, but instead is diffuse and has got sort of large scale structure, then most of the power of that source will be near the origin. V of U will be non-zero near the origin, and it will be zero everywhere else. There's an inverse relationship between the wavelength on the sky and the separation on the Earth. So we spoke about this being like a filter, right? So if I have antennas which are very far away, they're only going to pick up high frequency oscillations in the sky. But oscillations in space, not in time. So basically it picks up fine scale structure on the sky. If the antennas are close by, they will filter out all the fine scale oscillations and they will see only the long, meaning the sort of large scale structure of the source.
Sir, can you once tell what do you mean by fine scale structure and large scale structure?
Yeah, maybe I can just show it to you in a picture. That might be easier. All right, so maybe I'll just move ahead and then we'll come back to this. So see, here what I'm showing you is now the coverage of the GMRT antennas in UV space, right? That is, what I have is I have 30 antennas in that configuration, which I showed you before. I will track a source from rise to set. And as we saw, when we track a source from rise to set, the U, when we were working in one dimension, we saw that the U will change, right? Similarly, here, when I'm working in 2D, the U and the V will change, right? So what I'm showing you on this plot is U on the horizontal axis, V on the vertical axis, and every dot on this plot is one UV measurement, that is one baseline separation projected towards the source at one instant of time. Right, so this is basically all the measurements that I have made if I track a source from rise to set. And the plot on the left with a scale of 25 kilometers is if I only consider the pairs made by the arm antennas. I'm only plotting the data coming from pairs made by the arm antennas. And you can see that it gives me a reasonable coverage of that plane. That plane is reasonably well sampled, going out to 25 kilometers. but there's a hole around 1 kilometer, and that's because I haven't considered the points that I will get by made by antenna pairs in the central square. And that I have blown up, and I've shown you that here in that blow up over here on the 1 kilometer thing. So in the 1 kilometer, if I just look at what happens at inside 1 kilometer, where I've now only plotted the pairs made by the antennas in the central square, you can see those also give me a reasonably good coverage, right? So inside the central square, the coverage that I get, the sampling that I get is really completely dominated by those antennas. Whereas these antennas, since their largest separation is about 1 kilometer, they will not give me any samples outside 1 kilometer. The samples which come outside 1 kilometer are basically dominated by the pairs between the arm antennas. So, and when I put all of this together, and I also, of course, consider the pairs formed between the central square and the arm antennas, which I have not plotted here, I will actually get quite a nice coverage of this entire plane. And so I would have collected all the components, all the filtered in, or my filter would have collected all the spatial components, and I would be able to make a fairly high fidelity image of the sky. But what would happen if I were to use just one or the other? And that's what I'll show you in the next picture. So I'm showing you, Nessim had mentioned observations of acetaldehyde, right, where he was talking about how do you calibrate these observations, etc. These are those observations of acetaldehyde. And what I have shown on this image on, at the top left is the image that I would get if I were to only work with the central square antennas. And then I see that I have quite a large source, and I can see some structure in the source, etc. There's a blob here, there's a blob here, there's another diffuse blob here, and there's a further diffuse blob below that over there. That's what I see, but I don't see much structure inside each of those blobs because I've made the image using only the central square antennas, and they are not sensitive to any fine scale structure in the source. I don't see it. It just looks like a smooth blob in there. On the other hand, if I were to use the arm antennas, and now I'm just showing an image blown up of that small region over there, but now this image is made up using the data from the arm antennas. Then I can begin to see that actually what has looked like a smooth blob over there to me is indeed made up of multiple more structures. It's got more complex fine scale structure in it. I can see the fine details in that source. Does that make things a little clearer?
Yes, sir.
Anybody else have anything?
Yeah, so the significance of this white kind of configuration, I mean, what kind of configurations would be, if we were to design it differently, arranging in a different pattern, we would get a different image, or is it a different resolution?
Yeah, so the way in which I lay the antennas down on the ground will determine the way in which I would collect those points in the UV plane, right? It depends my sampling. This picture that I showed you over here, right? So that is determined by the way in which I lay the antennas down on the ground. That's determined by the way in which I lay the antennas down on the ground. And now there are very, you could think of laying them down in different patterns on the ground. It turns out, for example, that if I put my antennas on a circle, it actually gives me very, very nice, sampling. It gives me quite, it allows me to measure a very large number of points, and it gives me a good range, a good distribution of sampling, excepting with the following problem, that I have multiple measurements of the same visibility. It's what you would call highly redundant. That is, if for example, we are talking about making a measurement at 100 meters, I would have far too many 100-meter measurements. They repeat the same measurements far too many times, and I don't want to do that. I would like to have a good coverage of that plane. I would like to have minimum redundancy. That is, I don't want to measure the same point twice. I'd much rather try and put my antennas at some different separation, so I have a measurement at a slightly different point. So, for example, if I were to try spiral arm-like distributions, they will work out much better in doing that sort of thing. So many of the newer antennas are basically, they try and put, many of the newer arrays try and put their antennas in spiral arm-like configurations. There are two considerations when you are trying to figure out how to lay down your antennas on the ground. One of them is the fidelity of imaging. That is, that each whatever I put down on the ground will have consequences for the effectiveness with which I will sample the Fourier transform of the image, and that is an important consideration. The other important consideration is just practical considerations. That is, where all do I have land? Where can I put down my antennas? How much will it cost to put these antennas, to connect all of these antennas to a central processing station? Is there road access to the antennas, and so on and so forth. So you can see when I put the antennas down in a straight line, the problem of connectivity actually is greatly simplified, because I can run just a single cable trench along this line, and I can lay all the cables that I need to get to these antennas along that trench. Right. If I were to randomly distribute antennas, in this 25-kilometer area, I have to dig a separate cable trench to each antenna, and that can be a very, very expensive operation. So that kind of thing is manageable in a short distance, right? So within this 1 kilometer area, the antennas are put down in a semi-random fashion, and each one has a separate cable trench running to them. But because the distance is relatively small, the cost is manageable. And similarly, the exact location of these antennas on the ground would be determined by where is the nearest road, where is the nearest access point, and so on and so forth. So both of these considerations go in. You'd like to have your antennas along a Y-shaped arm in this particular instance, because a Y shape also actually gives you reasonably good sampling. That also is known from simulations. So that's why this particular Y was picked, because it gives reasonably good sampling. But it's not strictly necessary that they have to be in an absolutely straight line, because the small deviations around the line are not going to make a big difference to the sampling. So you could fiddle things around a little bit depending on the local topography. Is there a hill? Is there something on the way? Or is there, a river where I'm trying to put my antenna down? All these things. For that, you can just fiddle the location a little bit. And finally, based on both practical as well as these kind of astronomical considerations, you could fix the location.
Sir,
yeah,
I have a question.
Yeah.
So why is it that imaging is possible in optical astronomy using a single dish, a single mirror, but not in radio astronomy, and we need an array and a correlator?
Yeah, so that is related to the thing we started with, that if we were to use a single dish radio telescope, its resolution goes like lambda over d, which we saw is a few arc minutes, right? So whereas in an optical telescope, it will be of the order of few arc seconds, perhaps better, right? So if I were to put some kind of array detector on an optical telescope, right? So I put a CCD camera or whatever it is that I put at the focus of the optical telescope, I will be able to make an image of the sky which will have a resolution of few arc seconds. If I try and do that on a radio telescope, I could certainly put, we should put one feed antenna on the telescope, right? And we instead of putting one feed antenna, I could consider, in principle, putting an array of feed antennas. So I put a small array of feed antennas, and then I would make a 2D image at one go with my radio telescope. But what would its resolution be? Its resolution would be a few arc minutes, right? So that's not very interesting.
Okay, so it is possible in principle to have a very large single dish and have an array of feeds and have an image like in one observation.
Yes, it is.
Okay, thank you.
But it's not. But it's not practical.
Can you show those circular graphs once? What did they show?
So.
What quantity is plotted there?
Right. So you can see this plot over here. which has the antenna locations,
Yes, sir.
right? So now what I'm going to do is I'm going to observe the sky with these antennas, right? And I'll measure the visibilities. What does a visibility measure?
The conjugate product it measures
Between?
the first V1 into V2 star.
Between two antennas.
Yes.
Right? So for every antenna pair over here, I will get one measurement.
Yes.
Correct? I have 30 antennas. So at one time, how many measurements will I get?
32.
Which is 435. Right?
Yes.
So I get 435 measurements at a time.
Yes.
Now I have broken that up into subsets. And I have considered two sets of measurements. One set which come only from the pairs which lie, where the pairs formed by antennas inside this 1 kilometer by 1 kilometer.
Okay.
That's one set. The other set is what I get when I combine the arms with the arms. Okay. And at any one instant of time, I will get 435 measurements. But as we saw, if I track the source from rise to set, I'll get more and more independent measurements, right? Because that projected separation keeps changing as the source moves, right?
Oh, so the size of the dot represents the value of the visibility.
Not the size of the dot, the location of the dot shows you the point in I have made a measurement. So the location, this is the U-axis, and on the vertical is the V-axis. And so I have made a measurement. Wherever there's a dot, I have made a measurement.
Okay, so the darker means dots are closer.
The darker dots means basically they're closer. That means I made many measurements over there. Because what is happening, why am I making more and more measurements? Because the projected separation of the antennas is changing, right? As the source rises and sets.
Yes.
Right? Let me just go back to that very cartoon kind of, which I said, don't take it too seriously diagram, right? So this, you can roughly imagine this is what is happening, right? And so these things are rotating around, and you can see already that there are more dots in the center than there are dots elsewhere. And that's happening because, you know, at the center, that circle's diameter is smaller. The circumference of that circle is smaller. So I will get more points on that smaller circumference than I will get on the much larger circumference further out. That's all that's happening. Yeah. So that's why there are more dots towards the center.
Okay. Sir, how is it so well symmetrical and very circular type?
That depends on the location of the source, and I have picked the source to have a location where this looks more symmetric. Supposing I were to have the source, for example, on the Earth's equator, it really depends on the location of your array and the location of your source. Were I to put the source on the Earth's equator, things won't look so nice.
Okay. Sir,
yeah, that's a good question. You didn't get which?
What did you mean by fine scale structure and large scale structure?
Let me go again to this picture. It's a picture of the same object. The one which you see on the upper left and the one which you see on the lower right is an image of the same object.
Yes.
What you see on the lower right is what is this is not the full image that you see on the upper left, but only the part which is shown in the rectangle. That much is clear, right?
Yes.
But it's not just that I've taken that data in that rectangle and I've plotted it again. You can see that on the lower right, you can see much more detail. There are, you know, the contours. You have much more fine structure in those contours than I see on the in that picture on the upper left. Right? There's more structure in the picture on the right. Okay,
so for minute details, we will require larger wavelengths.
Larger separations of antennas.
Oh, okay. Yes.
Right? Because that's what sets the angle, whether you see fine structure or not. So if I have, you can easily see that, right? I mean, even if intuitively, since we saw that the angular resolution depends on the antenna separation, if I want to have fine angular resolution, I better have large antenna separations.
Yes.
Right. So these antennas at very large separation will allow me to make images with very fine resolution, and I can see the fine details. But what is not obvious is that if I only had antennas at very large separations, I actually would not see the diffuse emission. So if you look at the picture on the lower right, you can see it actually shows only part of that emission. The emission which you see in this main picture, actually it's diffuse, right? It fills up that a large fraction of that box. A large fraction of the box is filled by contours. A large fraction of the box is not filled by the contours when I zoom in. And that's because that zoomed in image doesn't have sensitivity to that diffuse emission.
Yes.
Right. So if I were to focus only on the large antennas at large separation, I won't be able to see the diffuse large scale structure. I miss it. I think that if I were to look only at the lower picture, I think that, there's a roughly arc like the acetaldehyde molecules in this cloud are basically only in this arc. But if I were to actually take a look with the central square antennas, I realize no, that's not true. That there is, in fact, also diffuse emission, which is widespread through the cloud. The molecule is actually present everywhere in the cloud. It's just that there is some concentration over here, which gives me this fine scale structure, which is, for which I'm seeing these variations in concentration or variations in emissivity, which are concentrated in that part, those parts.
Then why are we not directly plotting the fine scale structure? Why are we going for the slow scale structure?
The large scale structure. They are complementary pictures. That's the point I've been trying to make. That it is, the picture which you have on the upper left does not show you the fine details. The picture that you have on the lower right does not show you the diffuse emission. And you can pick, that's the way radio astronomy tends to work, because we are working with a filtered set of images, right? You can decide what kind of filter you want to use, but you can't, but you have access only to the filtered image.
Sir, so is there any way to get a clearer form of the above image top left?
To get a finer resolution? Yeah, it's so part of it, no. Could you rephrase your question?
This image is quite blurry, so can we just...
It is not blurry. Partly it is blurry. It has smoothed over, you're right, it has smoothed over the fine scale structures, but there is something more it has done. It has actually picked up emission which is widespread throughout the cloud. It has found that there is emission everywhere in the cloud.
Yes, sir.
Whereas the one on the right has only picked up the areas of that cloud where there is rapid variation in the emission.
Yes.
So, sir, if we have the large scale structure plot on the left side, so if we want to look into some other like concentrations, for example, in the area you have highlighted, just on the below it on the right hand side, there's another black concentrated dot. So does it allow you to look at different areas of fine?
This one?
Yes, sir. And then also
it would allow me to do that also. I haven't plotted it, that's all.
Okay.
I can zoom in on whichever bit of the image I want. It's just I've just shown you one piece that we zoomed in on.
Okay.
Sir?
Yeah.
Is interferometry and aperture synthesis like a very active field of research even now, or like?
Yeah. All the techniques are all set. Yeah. So that's a good question. Maybe I'll just, I am over time, but with Sykes' permission, I'll take a few minutes more and just wind up to talk a little bit about that. Yeah. So let me just go back to this figure. So this basically, as we have been discussing, the points over here tell me where all I have measured the visibility function V, U, and V. Wherever I see a point, there I have a measurement. I have no measurement elsewhere, right? So it's not like I've actually measured the function everywhere in the UV plane. To measure it everywhere in the UV plane, I would need to know the function at all points all the way from 0 to infinity. I don't have that. I have it only up to about 25 kilometers. Beyond 25 kilometers, I have no information. And even inside 25 kilometers, I only have it at discrete points, points at which there happen to be antenna pairs at some point in time, right? So so I have a finite set of measurements. The integral that we wrote down, that Fourier transform, which was invertible, assumed that I know V of U, that I know V of U from minus infinity to infinity, and I know it everywhere in the UV plane. That, in fact, is not the case. I actually know it only over a finite set of points. So I have not measured V of U, which is this thing which I've shown you over here, but I've measured only V of U at some discrete locations, which can be given by a sampling function, S of U and V, right? And that's the sampling function that I have written down over here. That it's basically 1 wherever I had an antenna pair, and it's 0 wherever I don't have an antenna pair, right? So what I have access to, what I have measured is not the true visibility function. What I have measured is only a sampled version of the visibility function. So the best thing I can do is to take the inverse Fourier transform of whatever I have sampled, because that's all I have in hand. So what I can do is then I take an inverse Fourier transform of the sampled visibility function. And, for those of you who've done Fourier transforms, the net result is that it would be the convolution of the Fourier transform of the true visibility function convolved with the Fourier transform of the sampling function. So that means the Fourier inverse of the true visibility function is the true image that I want, IL of M, but that's not what I measure. I measure IL of M convolved with some particular function, which is the inverse Fourier transform of the sampling function, which in the jargon is called a Doty beam, right? So to just give you an idea of what these things look like, right? So this is a true image, that's what I want, but what I actually get is the thing convolved with what is called the Doty beam, right? So to give you an idea of what this would look like in practice, here it is, what it would look like for the GMRT. This is the true source. This is really the image which I would have liked to get. This is the inverse Fourier transform of my sampling function, right? And so what I actually measure is the left image convolved with the right image, which is what I've shown you at the bottom, right? So you can see it's actually quite messy. And here I've put only one source in the middle, but you can easily imagine that if I had a second very faint source over here nearby that first source, but much fainter than it, that second source would get completely lost in all of this muck, which comes about when I convolve with the Doty beam, right? So I would actually be very severely limited in being able to actually see faint sources in the presence of bright sources. So what you'd ideally like to do is to find a way to correct for all of this. And in a sense, you can, because you can, as you can readily imagine that, this second function on the right, which is the Fourier inverse of the sampling function, is a function which I know, right? Because I know where all the antennas were. I know what that sampling function was. I can compute its Fourier transform. So I know the way in which the image has been distorted. So I could try to use that information to, in some sense, correct this image. And so that process, which unfortunately is complex and poorly understood, is called deconvolution. It's a general class of problems. It's mathematically, unfortunately, ill-posed, and it's called deconvolution. And there's unfortunately no mathematically rigorous way to do it. Even though, I've sort of know BDLM, I will not be able to. It's not clear that even though IDBLM and BDLM, I'm sorry, I've got a typo over there, are both known, it's not possible to mathematically rigorously derive a way in which to do that correction. Instead, one relies on a host of reconstruction techniques, none of which are guaranteed to give the unique correct answer, right? So you want to do some operation on, I've shown you the image, the dirty beam on the top. In the middle, I've shown you the dirty image, that is the true sky convolved with the dirty beam. And I want to do something to these two images to get back the true sky. And that's something that people do is called deconvolution. And I don't have the time to get into deconvolution algorithms, but except to say that, there are classical algorithms which are widely tested and well used, but it remains a topic of active research. And a bunch of things that people throw at it. And in the recent past, people have also been trying to try approaches like deep learning and so on and so forth, to try to extract from the top two images what the true sky would look like. So it's a topic of active research in which, there's a lot of work which has been going on, particularly in the last decade or so. The other problem which I haven't talked about is that we've assumed everywhere that our measurements were perfect, they're perfectly calibrated, there's no problem, and so on and so forth. But in fact, our data will be highly imperfect. And one of the imperfections, which particularly at low frequencies are bound to hit you, is that the radio waves, by the time they reach your antenna, it's not that they've propagated through a vacuum, right? They've propagated through the plasma, which is tenuous in interstellar space, and that typically doesn't have such a major problem. But it's also propagated through the much more dense plasma in our ionosphere. And because of that, because of propagation through the ionosphere, there are phase errors across your array, because the ionosphere introduces additional phases which you don't know to the ray as it propagates through the ionosphere. So the net result is that you will get a blurred image. It's a little bit like seeing in optical astronomy, right? And I won't, again, given the time, I won't go in through all of this. I'll just, okay, maybe I'm showing you the final. Maybe I should just say this a little bit carefully to you all. See, if you assume that the ionospheric phase, whatever error that the ionosphere has produced, is a constant across the field of view, then for an N antenna system, you'll have one unknown phase error for every antenna, right? So every antenna, the ray which reaches that antenna has got a phase error because of the propagation of that ray through the ionosphere, right? So the number of instantaneous measurement numbers which you have to calculate to do the correction is just N. On the other hand, the number of measurements that you made is NC2. Right, so you have NC2, which for a large N is much, much larger than N. So for example, for the GMRT, you have 435 measurements versus 30 antennas, right? So there are 30 unknowns, which are the 30 unknown phases introduced by the ionosphere, but you have 435 measurements. And so, since this is a highly over-constrained problem, it's actually possible to sort of make corrections for the ionosphere. And particularly if you have a model for the source, you can use that to estimate the antenna phase errors. And once you've estimated it, you could refine the model of the source, and you can keep going round and round until you converge onto a solution. And because the problem is so highly over-constrained, you will typically converge to the correct solution. So I'm just showing you that over here, two sets of images made with the GMRT. The one on the left is the raw image that you make, where you haven't corrected at all for the ionospheric errors. You can see, the distortions that you see in the image. And, this is an iterative algorithm, and I've shown you what happens just after one round of that, one iteration through that algorithm. And you can see how significantly sharper those images are, right? And again, this is an area. I'll just run through this and, go ahead. Please go ahead.
So self-calibration refer to.
I'm sorry, your voice is breaking.
Sir, the self-calibration which is mentioned here, does that refer to the deconvolution process, or is it something different?
It is something different from the deconvolution process. The deconvolution process, you are correcting for the fact that you have access only to sampled data, not the full data. You would really like to know the visibility function from 0 to infinity. You don't have access to that. You only have access to a sampled version of it. Deconvolution is correcting for that. Self-calibration is correcting for the fact that your rays have propagated through the ionosphere and have therefore acquired extra phases because of propagation through the ionosphere whose refractive index is not unity. You don't know what that extra phase is, but it turns out that you don't need to know, you can still correct for it.
Okay, sir.
Yeah.
Color assigned to the image.
Sorry?
This is taken at radio wavelength, so how is the color assigned to the image?
It's just brightness over here. It's a black and white image, as you can see, a grayscale image, and the brighter light, the brighter just corresponds to, I mean, if it's brighter, it's just the emission is stronger. That's all.
Okay, sir. Okay.
Yeah, and to finally end up with the question that was asked, that is aperture synthesis all done and dusted. It's far from true. And I want to just take an example by talking about the evolution of the GMRT, right? So when the GMRT was originally constructed, it had these 4 feeds on this turret, and each one of them covered the frequency range that we are talking of, which I've shown you over there. But more importantly, it supported a maximum bandwidth of about 32 megahertz, right? Which is a small bandwidth. So at that time, the fractional bandwidths were small. Now the GMRT, which has got upgraded, and I'm showing you over here the frequency coverage of the upgraded GMRT, and you can see that the fractional and the instantaneous maximum bandwidth has also changed to 400 megahertz instead of 32 megahertz. So you can see that the fractional bandwidths are no longer small, right? So for example, if I'm talking about the 250 to 500 megahertz, I'm going to observe that entire range at one go. So the range that I observe is from 250 to 500 megahertz. That's a total of 250 megahertz. And that is comparable to the 250 megahertz of the lowest frequency over there, right? So I'm no longer observing a bandwidth which is small compared to the center frequency. I'm observing bandwidths which are comparable to the center frequency. Right, so all of this makes a big difference to the way in which you are able to process the data. And, we looked at one of the assumptions when you do this aperture synthesis, which is namely that the field of view should be small. But there are a number of other assumptions which we didn't go into detail about. But these new radio telescopes that people are building violate basically all the assumptions of that were made at the beginning when we sort of derived all of these equations that we are working with. So the standard aperture synthesis assumptions are violated by almost all the new telescopes, including the upgraded GMRT. So the first is that the field of view should be small. We haven't talked about this, but the next generation of radio telescopes, which is coming up, not the GMRT, but several others, including SKLO, LOFAR, and so on and so forth, MWA. The field of view can be as large as the entire visible sky, right? It could be very large. And in general, it is typically quite large. And in principle, you could have fields of view as large as the entire visible sky. The other assumption that I didn't go into in detail, but which is required, is that the bandwidth be small compared to the center frequency. As we saw right now, the bandwidth is comparable to the center frequency. So that assumption also is broken. The third is that all propagation and instrumental effects have been corrected. And it turns out that, the level at which you have to make these corrections depends on the sensitivity of your instrument. If my instrument is not very sensitive, for example, I would maybe able to live with 10% errors, because 10% errors are much smaller than the noise in my instrument. But as I make my instrument more and more sensitive, I have to be able to calibrate it and correct these errors more and more accurately. And that's the issue that we're having over here, that the instrument has become much more sensitive, and therefore sources of systematic error which could be ignored earlier are no longer ignorable. And these include spatial variation in the phase produced by the ionosphere, angular variation in the instrumental sensitivity. We haven't talked about it. When we talked about the field of view, we pretended as though the instrument was equally sensitive over its entire field of view. That is not the case. One would have to deal with the fact that the sensitivity varies over the field of view. Variations in sensitivity, because the telescope is jittering in its pointing. We are assuming that this telescope is tracking the source perfectly, but this is a large mechanical structure, right? So it won't track it perfectly. It'll jitter a little bit. All of those will produce errors. in your image. And so this is, in a sense, the frontier where people are working on to correct all of these so that you get more and more, better and better fidelity of your radio images. So maybe I'll stop over there. I've overshot my allocated time by a long time. I'm sorry about that. But if Sykes feels it's still okay, we could take a question or two.
Yeah, I think you can take a couple of questions, a few questions. Yeah, it's fine. Or Jayaram. So you can unmute yourself and ask the question as you've done.
Sir, how do we know or how do we get the sampling function?
The sampling function we know because we know where the antennas have been placed on the ground, right? The sampling function depends on the separation between the antennas, because wherever I have an antenna pair, I have a measurement, and where that's all that defines the sampling function, the location of your antennas on the ground. Of course, we have to project it depending on the location of the source that you're looking at, because it's a projection. It's a projection of that separation towards the source. That is, since I know which source I'm looking at, that projection also is easily calculatable.
Okay, understood. Thanks.